All right, so this is lecture 24. Sorry, still fiddling with my Zoom settings. Oh well. This is lecture 24. The topic is, man, sorry, still fiddling with them. All right. Sorry, everybody. Edit out all these words and put in new words. All right. Great. So this is lecture 24. This is going to be about information theory. So information theory has a classic textbook by Cover and Thomas, but there's more modern stuff out there, which we'll talk about a little bit. And it includes a lot of nice works by Braverman recently. One more time. All right. Okay. So today's topic, information theory, there's lots we could talk about. I'm going to talk about some of the basics, just definitions about entropy and mutual information. And then we'll see one application, information complexity, that's an application to communication complexity. So I'm doing the application so that it connects with previous lecture. Okay, so let's start out with entropy. So all this topic, information theory, was developed almost in one shot by Claude Shannon in 1948. In particular, he gave this definition of entropy, which we're going to describe now. So let's start with an example. Let's say that x is a discrete random variable. It takes on finitely many values. So in this example here, x takes on the values red, green, blue, and yellow. And the probabilities are as shown up here in this example: half, quarter, eighth, and eighth. So first I'll tell you what the entropy of this random variable is intuitively. So the entropy is usually denoted h of x. It's a number associated with the random variable. And one way to capture it intuitively is to say it's the amount of randomness in x in bits. Another intuitive way to describe it is it's the minimum number of bits needed to generate a draw from x on average if you're using the best scheme. So imagine that you needed to write a computer program that output draws from this random variable x with these specifications, and the only thing you're allowed to do is flip a fair coin. How many coins are you gonna have to flip on average with the most efficient program? This is what we're asking ourselves. So one scheme you can do for this particular x is first flip a coin, and if it comes up heads, you can output red, because red is supposed to come up with probability half. If it comes up with tails, then you can flip another coin, and if that one comes up heads, you can output green. So then green will correctly be output with probability a quarter, and so forth. You can flip one more coin to decide between blue and yellow. And now we're going to compute the expected number of coin flips your program used to generate this random variable x. Well, with probability half, you used one coin flip. It's probably a quarter, you finished in two. And well, with the remaining probability, you finished in three. So if you add this all up in expectation, you get on average 14/8 or 1.75 coin flips. Okay, so the entropy of this random variable x is going to be exactly 1.75. Another way to describe it is it's the minimum number of bits you need to store a draw from x on average using some kind of compression scheme. Actually, in many ways, there's not a lot of difference between communication and generation and compression. So you could use that scheme that we talked about to generate x and just record the coin flips you used and use this as sort of like a code by which to encode a draw from x. So for example, if you're trying to draw, code draws from x, you could say, all right, red, I'm going to write down heads. Green, I'll write down tails, heads. Blue will be tails, tails, heads. Yellow is tails, tails, tails. And, in some cases you're using 1 bit. Some cases you're using 2 bits. In some cases you're using 3 bits to record this variable's outcome. And this is a nice example. The scheme here is what's called a prefix-free code, which means if you're drawing several instances of this random variable x and getting a sequence like red, blue, red, green, green, you can just write down these encodings with heads and tails with no additional punctuation in between them, and you can recover any sequence. So like tails, heads, tails, tails, heads, heads, heads. If you look back at this chart, it means first you flipped, let me get my little pen out. First you flipped green. The first draw of heads was green, And then the second draw was blue, so you wrote down tails, tails, heads. And then you flipped an H, and got, so you didn't flip an H, but you got a red, and so you recorded it with heads. You got another red, but recorded it with heads. Yet another way to think about it intuitively is that imagine, your friend took a draw from this random variable X and got like either red, green, blue, or yellow. And then you had to like play 20 questions with your friend to determine, what their outcome was, red, green, blue, and yellow. And you had to only ask yes, no questions. And it would be like sort of the minimum number of questions on average you would need to correctly determine what their outcome was. There's a question, do you always mean, the question from the audience is, do you mean there's always a prefix-free encoding which is the best? Well, actually, there is always a prefix-free coding that is the best. And in this specific case, as we'll mention in a second, I chose an example which has a very special property, namely, all the probabilities are powers of, inverse powers of 2. In that case, the analogous thing to what I did for a general random variable leads to a prefix code, which is the best. When you don't have this powers of 2 thing, it gets more complicated. And as somebody else pointed out in the questions, the best thing you can do is something called Huffman codes, which we won't actually get into in this lecture. This is also a particularly trivial example because, like, if you think about this yes/no 20 questions version of it, then like the optimal strategy is kind of a very silly strategy where like the first question should be like, well, is it red? And if it is, then great. If it's not, then your next best question is, was it green? And then your next best question, if not, is, was it blue? But you can have a more complicated scenario with a more complicated random variable. So as I mentioned, yeah, so all of these, intuitive definitions of entropy that I've given so far are actually exactly, correct if X does satisfy this special property that all the probabilities are inverse powers of 2, like 2 to the minus k for some natural number k, then all those intuitive definitions are exactly correct. And this would be the formula that you get. You just imagine, for example, the sort of the example we saw with the heads and tails. You imagine the expected number of coin flips your program would need to generate a draw from the random variable X. And you kind of go through each possible outcome, red, green, blue, and yellow. Those are the little x's here. And there's some probability that I've denoted P sub capital X of little x. So capital X means the random variable. Little x means like an outcome, like red, green, blue, yellow. And there's that probability that you would be trying to generate that outcome. And then the number of, coin flips you needed was like, the log base 2 of the reciprocal, right? So like blue corresponded to like, I don't know, tails, tails, heads or something, corresponded to 3 flips, which is like log base 2 of the reciprocal of 1/8. So probably you've seen this formula before at some point. This is the definition of the entropy of a random variable X. It's given by this formula. And okay, we can imagine applying it to maybe a different discrete random variable X, like this one, where the probabilities are not like all like, negative integer powers of 2. So like, X is A with probability a half, B with probability a third, C with probability 1/6. Now, if you imagine like trying to write a computer program that generated draws from this distribution X, or like you tried to, communicate a draw from this distribution to your friend by sending as few bits as possible. Well, things start out well with this probability of a half. With probability of half, you can, communicate or store 1 bit. But then with probability 1/3, you would want to try to send or store or use like log base 2 3 bits according to the formula. And that doesn't really make sense because that's not an integer. So you don't have like a perfect correspondence between the intuition and this formula in case that, these probabilities have the property that like log base 2 of the reciprocal is not an integer. But, you just go with it. I mean, you just accept it. And so this is the formula that gets used for any random variable X. And then it doesn't have like an exact perfect correspondence with these intuitions that I've mentioned before, but they're good intuitions. In fact, we'll see in a moment how like you can make them even more precise, these intuitions. So just on the topic of this coding situation, like if you want to store like a bunch of draws from this random variable as bits, one thing you can do is just take the ceiling of all these quantities to make them an integer, and then it's okay. So like you could have a scheme for storing, like say, draws from X, where you'll use heads to store, A, and tails heads to store B, and tails heads to store C. And then it's a bit wasteful because you're not using the sequence tails, tails, tails for anything. But that's life. And this is a pretty good way to, compress a bunch of draws from a random variable into bits. This naive way of, I haven't exactly defined it here, but I sort of sketched it, is called the Shannon or Shannon-Fano code. And it's a pretty good scheme. As mentioned by somebody else in the chat, there's actually a better scheme that uses fewer bits on average called the Huffman code. It's sort of the optimal scheme in general. But this scheme where you sort of just like pay up to 1 extra bit per draw due to the fact that these logarithms are not necessarily an integer is not such a bad scheme. So in general, how many bits do you use on average if you try to store your draws from your random variable or communicate draws from your random variable in this way? Well, it's sort of the same formula, except you have this like ceiling in here. And this ceiling is at most what you get if you take the actual real number and add +1 to it. And so if you look at this expression here, and like you break it up into its 2 parts, the first part, when you expand out, gives you the actual entropy term, this thing here. And then you get plus the sum over x of p of x times 1. So that's just +1. Okay, so overall, this simple method of encoding or generating or storing draws from a random variable x uses a number of bits, which is at most the entropy +1. Okay, so as always, if you have questions, do type them into the chat. Question is it hard to determine if a given encoding scheme is uniquely decodable? Whether it has these schemes we were mentioning have this property that's different from the situation when we're talking about coding theory. The difference is that the number of bits you use to encode a message or a draw is not always the same. It's like a variable length encoding. And there, if you're not going to use punctuation, then you need but you do want a variable length encoding, you need your scheme to have this prefix-free property where no code word is a prefix of another code word. That, of course, is easy to check if you have a whole list of code words. And if your code has that property, then it can be uniquely, and like a sequence of encodings can be uniquely determined. It can, be turned back into. There's a unique way to break it up to get code words. Yeah, the question is non-prefix-free codes can be uniquely decodable. Yeah, probably, possibly. I'm not 100% sure, to be honest. Okay. All right, so this is the formula, and let's, if you haven't seen it too carefully before, let's go over some basic facts about it. So, okay, it's a number that's associated with a random variable that somehow measures like how many bits of information a draw from it carries. And so here's some basic facts. I'm going to ask you to fill in these blanks in a moment, so think about those. Let's say your random variable x can take on one of at most capital N values. Then it's a fact that this entropy is at most log base 2 of capital N, and it's always non-negative as well. So it's at least 0. Okay, so we can think about when these two inequalities are sharp. So feel free to type into the chat the situation, what random variables x have 0 entropy, and which random variables have log n bits of entropy, where n is a bound on the number of outcomes. Yeah, so a couple of people have said it correctly. That's right. So the first case, a random variable has 0 entropy if it's constant, if it's not really variable, if it's always the same value, or it has like a probability of 1 of some outcome. And has maximal entropy log base 2 of n if and only if it's uniform on the n possible outcomes. They each have probability 1 over n, and that's true whether or not n is a power of 2 or not. Good. So it's sort of the least variable and the most variable random variable. And there's a lot of, when you're proving things about like entropy and other elements of information theory, there's like a lot of like little exercises that involve like writing down expressions with like logarithms in them, and mainly using the fact that like the logarithm function is convex, or like the logarithm of a reciprocal function is concave, and using, you know, Jensen's inequality and things. So I won't prove it. I'll only do like maybe one of these proofs, but like the proof of this fact, the second fact, is an exercise for you using concavity. Okay, so let's go back to this slight annoyance where we saw that, like, let's say we have a random variable x and it doesn't have this, you know, pleasant property that all the outcomes have a probability that's like 2 to the minus k for some integer k. And we saw that, like, if we want to, you know, compress a draw from this random variable x, we could, you know, invent like a simple scheme where the number of bits like stored on average or communicated on average, if we're communicating it, was at most the entropy plus 1. And the plus 1's kind of annoying, but there is a way to get rid of it and to kind of get around this fact that, you know, I mean, ultimately number of bits has to be an integer. And that's the thing about the idea of amortization, or about like what happens if you're going to repeatedly draw from this random variable and store like many copies of it, or repeatedly get draws from this random variable and communicate it, and to think about like how many bits on average you have to communicate. So let me go into some more detail about that. So let's start with what's like a sort of simple fact. Let's say that x and y are independent random variables. So this independence is going to be important for what I'm about to say. So you can view the pair x comma y as itself as a single random variable. Okay, you just say, oh, I'll stick x and y together and call like that one object also a random variable. And it's often, or at least in information theory, often just denoted by concatenation as though it were a string, x, y. And when x and y are independent, it's not hard to check from the formulas that the entropy of the joint random variable x, y is just the entropy of x plus the entropy of y. And here's the intuitive proof of it. You know, if you take the viewpoint that, like, okay, entropy is the number of, you know, random bits you would need if you're writing a computer program to generate a draw from the random variable in question. Well, I mean, on one hand, if you want to generate a draw from this random variable x together with y, like one thing you could do is take, you know, the most efficient program for generating a draw from x and the most efficient program for generating a draw from y, and like just run both of them. And now you've got a draw from like x and y independently. And, you know, the total number of bits you used on average was the sum of the number you needed for x and the number you needed for y. So in some sense, that's like an upper bound that would show that, or that would give a sketch of why we have the upper bound here. And as for the lower bound, just basically, I mean, if x and y are independent random variables, like there's no savings that are possible. There's nothing you can really do except separately try to generate x and separately try to generate y. So this is an intuitive proof, and like this is the kind of proof intuitions that like get you very, very far in information theory. Ultimately, you know, you have to write down proper mathematical proofs, which look more like this. So as I said, I'm going to show you this one proof, and then I'll just rely on intuitions for most of the other facts that we talk about. Because in most cases, like these proofs are kind of like an exercise in like manipulations, and they follow the intuition. So we can, you know, write it on the definition since we're doing, you know, a first example here. Okay, so by definition, the entropy of the joint variable x and y is, well, you sum over all possible outcomes for this random variable x, y, which consists of pairs, little x and little y. And you get the probability of seeing this pair, little x, little y, times log of 1 over the probability of this little x and little y. And now we crucially use the fact that we're assuming the random variables x and y are independent in this story, which means that well, it means that this equality is true, that like the probability of seeing some little x and some little y is just the product of the probabilities, the probability of seeing little x times the probability of seeing little y. And we can also break up the sum into a double sum, because the range of possible values for this joint random variable xy is just the range of x together with the range of y. And then we use the property of the log function, that log of the product of two things is the sum of the logs. So we kind of made the same replacement about the probability of xy being the product of the probabilities here in this expression. And then we separated that into a sum. And then in this next line, I kind of ask you to imagine, like, expanding or distributing across this sum. And you'll get a term that looks like the sum over x and the sum over y of px, py, and then log 1 over px. So if you put all that x stuff together, you get the entropy, the expression for the entropy of x, but you also have the sum over y where you're just summing the probabilities. But luckily the sum of the probabilities of y's is 1. Okay, and that gives you this term. And similarly, this second logarithmic expression gives you the entropy of y times the sum of the probabilities for x, and that's 1, so you get this h of y. Okay, so that is the formal proof of that equality. Okay, and you can iterate this, and so as a corollary, you get that, let's say you have n independent random variables, then the entropy of that single random variable that you get by like just treating them all together is the sum of the entropies. And in particular, if you have like one random variable called x, and you make like n independent draws from it, and thereby get like sort of copies, x1 through xn, independent copies of this random variable x, then the entropy of like all those draws together is just n times the entropy of like a single copy. Okay, so let's remember that fact. Because it relates to this amortization that we were talking about, like imagining, instead of storing or communicating or generating one copy of x, like let's imagine storing or communicating or generating like, a large number n of independent copies of x. So, okay, so let's say you were trying to store or communicate n draws from some random variable x. Well, one thing you could do is you could say, okay, I know like a scheme for communicating like one copy of a draw of x, and it used like entropy of x plus 1, in the worst case, many bits. So then if I need n copies, I could just do n times that. So the total number of bits I would get is n times the entropy plus n, which is okay, actually, but it is a little bit wasteful. So as an example, like let's say x is a uniformly random trit. It's 0 with probably a third, 1 with probably a third, and 2 with probably a third. So the entropy of that random variable is 1.6 bits, log base 2 of 3. You can check. And so this scheme that I mentioned here, basically uses 2.6 bits on average per trit. It'd be like it would encode like 0 with heads and 1 with tails, heads, and 2 with tails, tails, or something like that. And so overall, you'd be using 2.6 n bits on average to send n trits. You can see that's kind of a waste, because really, if you have n draws from this random variable x, it's like you're getting like a random number written in ternary with n ternary digits. So it's like basically a random number between 1 and 3 to the n, or 0 and 3 to the n minus 1. You should really be able to encode it with a number of bits that's like basically the log base 2 of that, which should give you this log base 2 3 per bit, like 1.6n bits. And so you see, using this corollary up here, you can do something different, at least in principle. You could instead say, wait a minute, like let's just treat this x1 through xn as like one single random variable whose entropy is 1.6 times n by this corollary. And now we could have a scheme for generating or communicating or storing a draw from this like n-fold random variable. And the number of bits we use would be the entropy, n times the 1.6, the base entropy, just plus 1. Okay, so instead of plus n, we got like plus 1 if we kind of batched these draws together into groups of n. And that's kind of cool because then if you, divided this quantity by n to sort of see the number of bits per batch that you, or per draw, I should say, that you used, it's like exactly the entropy plus, now instead of plus 1, plus 1 over n, which is tiny. It's like going to 0 as it's little of 1 as n goes to infinity. So by using a different scheme where you like group your draws together into big batches and encode them using some kind of binary encoding scheme like this Shannon-Fano code, you can get into a situation where like the number of bits you communicate per draw of x, like in the long run, is asymptotically close to the entropy h of x. So this kind of shows that like h of x is sort of exactly equal to like the amortized cost of transmitting one draw from the random variable x, if you're allowed to amortize over like a large number of independent draws. Okay, so this box, I guess, is what I just said. Okay, so actually that's the last thing I want to say about entropy for now, and then we're going to move on to another topic in information theory, sort of the next step, which is mutual information. So as always, if you have questions, please chat them. Okay, so let's move on to talk about another topic in information theory, mutual information. And once we define this, it'll lead us into the third topic for this lecture, which is connecting everything with communication complexity. Okay, so let's say x and y now are random variables, but they're not necessarily independent. They're possibly dependent. And so now let's say I ask you, okay, write me a computer program that uses random bits, and it's supposed to generate draws from this joint random variable x and y taken together. Well, then the number of random bits needed to generate this pair is sort of ideally, or in the amortized long run, entropy of xy. As we saw, the last thing we talked about was that if x and y are independent, then this is just h of x plus h of y. There's no way you can sort of get savings. I mean, they're independent, so you basically have to spend your bits to generate x and spend bits to generate y, and that's all you can do. But if they're not independent random variables, you may possibly be able to get savings beyond this h of x plus h of y. And this savings that you can get, or sort of the most savings you can get, is exactly this quantity called the mutual information between x and y. So this is, again, a number. It's denoted I of x and y with, for some reason, a semicolon instead of a comma between x and y. It's a number associated with a pair of random variables, x and y, which you imagine are definitely not necessarily independent. Again, what is it? It's h of x plus h of y, which is like how many bits you would have to, a computer program would have to spend to generate a pair, the pair xy, if x and y were independent, minus the actual like optimal number of bits you need to generate x and y together. So it's sort of the savings you get by the fact that x and y are dependent. So let me, I mean, it's best to really not focus too much on these formulas involving logarithms, which is sort of suggested before. But anyway, if you write down the formula, you see that it's got this expression. The sum over all possible outcomes, little x and little y, the probability of little x, little y. This piece gives you, that eventually leads to the h of x term. This piece leads to the h of y term. And this piece, which is subtracted, leads to this term. And then by properties of logarithms, you can turn it into this expression here. And the main reason for writing this down is like this expression you can use to formally prove that the mutual information is non-negative. Okay, so if you think about it, it's kind of clear that it should be non-negative because it's supposed to represent a savings, which is like a non-negative quantity. Okay, so let me give an example. So here I have the complete sort of, not truth table, but like probability table for two random variables, x and y, which are not independent. And x can take on the values heart, 0, or 1. Y can take on the values heart, A, B, C, or D. And it's like this. It's probability a half. They're both heart with probability 1 over 16. X is 0 and y is A, and so forth. Okay, these numbers add up to 1. Okay, so let's compute everything just to get like a feel for these numbers and quantities. So let's first think about like the entropy of x. Like just imagine like you did a draw from these things, but like threw the outcome of y in the garbage and only thought about like the random variable x. So then basically you would see this situation here. The random variable x is heart with probability a half, and it's 0 with probability a quarter, and it's 1 with probability a quarter. Okay, so you have a random variable that's probabilities are like a half, quarter, quarter. So its entropy is like a half times 1 plus a quarter times 2. That's the log base 2 of reciprocal of a quarter, plus another quarter times 2. So that all comes out to 1.5. Okay, so x has like sort of 1.5 bits of information. Or if you only had to generate x, it would take you 1.5 bits on average. Right, because actually it's quite easy. You flip a coin, if it comes up heads, you'd be like, x is heart. Otherwise, you flip one more coin to decide if x should be 0 or 1. So half the time you're flipping one coin, half the time you're flipping 2 coins. So on average, you flip 1.5 coins. Conversely, if you look at this random variable y and just ignore x, it's heart with probability 1/2, and it's a with probability 1/8, because these are the two outcomes where it's a. And in fact, it's a, b, c, and d all with probability 1/8. So its entropy is, this simple calculation, it's 2. Okay, so if you just needed to generate y, it would take you 2 coin flips on average. Okay, and so therefore the sum of the entropies is 3.5. But if I said, run me a computer program that generated x and y together according to this distribution, and try to minimize the number of random bits you need, you could do it with less than 3.5. So in fact, right, it's just like sort of the entropy formula applied to this column. Sorry for the terrible circling, but a random variable that's probabilities are half, 16, 16, 16, 16, 16. So it's like half times 1 plus 8 copies of a 16th times 4, which is 2.5. Okay, and therefore, finally, the mutual information is 3.5 minus 2.5, which is 1. Okay, and let's check that this makes sense. This is supposed to represent like the number of shared bits, or sort of the number of the amount of savings you can get by virtue of the fact that you're generating x and y together as opposed to like independently. And it's pretty clear, right? In fact, the way you would generate this random variable is like, first you flip a coin. If it came up heads, you'd be like, okay, both of them are heart. Otherwise, if it comes up tails, then if you like peer at the rest of this table here, you actually see that they're independent. Like once you've decided that they're not both hearts. Okay, and so like x, you generate independently from y, you flip a coin, and for y, you flip 2 coins to tell if it's A, B, C, or D. Okay, so in other words, it's sort of like, it's the number of shared bits in your like computer program for generating x and y together that you first spend to reduce to the situation where the remaining calculations or the remaining generation is done independently. So does this make sense? Okay, so we're going to study this mutual information a little bit to get a bit more of a feel for it. So let's see how big or small it can be. So this is also, as I mentioned, non-negative. And I'll ask you again to fill in the blank here. When is the mutual information 0? You can kind of tell based on the name even. What property must x and y have for the mutual information to be 0? Independent, that's right, yeah. We saw before, if they're independent, then the entropy of the joint random variable xy is the sum of the entropies, so the mutual information will be 0. Okay, so as for an upper bound, you could say to yourself, well, the mutual information is h of x plus h of y minus the entropy of x and y together, so the entropies are positive, so at most, an upper bound is h of x plus h of y. That's true, and I wonder if someone in the chat can tell me when this equality is achieved. This one requires a little more thought, so I'll take a nice sip of water. Yes, one person said when x and y are constants. That is correct. This is actually not a great upper bound. It's true, and sometimes it is achieved, but the only time it's achieved if like both x and y are constant random variables and all the entropies are 0, which is a very trivial case. And I think you'll understand this better when I just give the better upper bound, which is the better upper bound is an upper bound for the mutual information between x and y is whatever is the minimum of the entropy of x and the entropy of y. And the idea here is, remember, like, this mutual information is supposed to represent like the savings that you can get from the fact that you're generating x and y together, as opposed to like independent copies of x and y. And the most you can save is everything. So I mean, if the entropy of x is 3 and the entropy of y is 10, and now you're trying to generate them together, okay, you're going to need at most 13 bits, depending on whether or not, if you'll need 13 if they're independent. But if they're not independent, like at the very least, you have to generate y if you're going to generate x and y together. And generating y takes entropy of y, which in my little story example here was 10. So the most you could ever save is 3, which is the entropy of x. And of course, let me ask you again, under what circumstance, I should have reversed my example, but anyway, under what circumstance, let's say that h of y is the minimum, y has less entropy than x. When is it the case that the mutual information between x and y is equal to the whole entropy of y? It's like asking, when you're generating x and y together, as opposed to independent copies, when is the amount of savings you can achieve entirely, like sort of all the entropy of y? Yes, somebody has said in the comments correctly when, somebody wrote, I think you wrote it a little bit backwards. Somebody said x is the f of y, but maybe it's the other way around. It's when y is determined by x. Okay, so if y is determined by x, then you're in a situation where you can like generate x, which costs you like entropy of x bits. And then you don't need to spend any more bits to generate y because it's determined by x. So you in total spent entropy of x rather than spending entropy of x plus entropy of y. So like the amount you saved with entropy of y. Perhaps that'll be more clear with an example. So let's do an example. Let's say x is a random n-bit string and y is like the XOR of all the bits in x. So these are two dependent random variables. X is an n-bit string, y is the XOR of the bits. So x is an n-bit string, so it's uniformly distributed. The entropy is n. And y itself, if you only squinted and saw y and ignored the story on x, then y just looks like a random bit. So it has 1 bit of entropy. But if you were to generate x and y together, you can sort of see that the best thing you can do is just, the best thing you can do is generate x and then just compute deterministically the value of y. So you spend n bits to do that. And so your savings over the sum of these two things, you spent n out of a possible n plus 1, so your savings is 1, okay? It kind of makes sense, I hope, to say that the mutual information between this x and y is 1 full bit. It's like the entropy in y. Okay, so this was our example. And now I want to look at like a slightly less trivial example where y is not completely just a function of x. Let me just set up a situation where, x is not a function of y and y is not a function of x, but they're not independent. They have some dependence. And I'll just do it in kind of like a simple way. Like, let me just say now y is 2 bits. It's a 2-bit string. And the first bit of y is the XOR of all the bits of x. And the second bit of y is just like another independent random bit. Okay, just something meaningful about this example, just some simple one I randomly cooked up. So we could talk about like generating the pair x and y together, but let's take the, communication point of view. So let's say like it doesn't matter which analogy we talk about. Imagine you're going to like try to make a draw. You get a draw from x and y. You want to communicate the draw to someone using as few bits as possible. An idea is you could first communicate the common part. And I've drawn like a little Venn diagram here to try to illustrate this, like sort of spend enough bits for the joint amount of information between them, which is 1 bit in this case. And then having communicated the sort of the common part, a number of bits that's equal to the mutual information, then you kind of communicate or spend in generation terms, like the deficit of h of x that you need to make up x. And you also communicate the deficit, oops, I should have drawn it like this, the deficit from h of y that you need to communicate y. Okay, if you remember back to that example with the hearts, like there the mutual information was 1 bit, you can imagine first communicating the single bit that tells you, are they both hard or not? And then you got reduced to the case where if they're not, they're sort of independent of each other, and you had to like generate the rest for X and the rest for Y. So I say all this to motivate another definition. So there's this sort of almost the last definition or simple definition. The term we're defining here is the conditional entropy of Y given X. And it's sort of like intuitively the green shaded part of this Venn diagram region, or this piece here. Sort of the information component of Y that excludes the mutual information. So as a formula and as a formal definition, it's again a number. It's the entropy of Y, but minus the mutual information between X and Y. And as we saw from last time, the mutual information, it's always at most the minimum of h of x and h of y. So in particular, it's at most h of y, which implies that this quantity is non-negative. There's also the symmetrical definition, the conditional entropy of x given y. But let me just focus on this one. Right. So these Venn diagrams are, in information theory, are helpful. They can, when you have more than 2 random variables, they can be harmful. But when they have 2 random variables, they're generally helpful. Right. So here's this definition again: the conditional entropy of y given x. And we can just expand out this formula. I mean, just to get another formula, the mutual information of x and y is this: the sum of the entropies minus the joint entropy. So we plug that in, we get a different formula for the conditional entropy of y given x. It's the entropy of the joint random variable xy minus the entropy of x. Or like in the Venn diagram terms, right? It's sort of like the total amount of information content in this blob. That's like h of xy. And then you take away h of x, this circle, okay, and you get the green shaded region. And if you rearrange this inequality with this, you get like an expression which is called the chain rule in information theory, which is that the entropy of a pair of random variables x and y, it's like the entropy of x plus the entropy of y conditioned on x. Okay, so you'll see that get used quite a lot in information theory. And I just wanted to write like yet another, I mean, I'm just writing all possible rearrangements of this formula. So like another rearrangement of this formula is this. And it's giving like sort of an in-words description of the mutual information. So the mutual information between x and y is also the entropy of y minus the entropy of y conditioned on x. All right, so it's like sort of taking like this circle here, which is the entropy of y, and subtracting out the green part and getting the overlap part. And you can kind of read this h of y, entropy of y minus entropy of y given x. You can kind of read it in like English language terms. These are all like, you know, intuitive crutches to help you reason about quantities that you'll eventually reason about by arithmetic and formulas with logs and things. You can read it as like the amount of information gained about y knowing x. So, you know, it's like if a person like knows the outcome of x, let's like, you know, somebody draws x and y, and then Alice like comes to know the outcome for x. How much does she learn about the outcome for y? What's interesting about this is like this formula is asymmetric. I mean, x and y play a different role, even though we know the mutual information is a totally symmetric concept. Remember, it's entropy of x plus entropy of y minus the joint entropy. So it means, you know, we can exchange x and y. The left-hand side doesn't change, but the right-hand side does change. And so this is another formula for the mutual information. And it sort of says, in, you know, according to these definitions, the amount of info gained about x knowing y is the same as the amount of info about y knowing x. So that's maybe not the most, I mean, depending on how you look at it, that might or might not seem intuitive, but it is true under this way of looking at things. Okay, so I just put these formulas up here and the Venn diagram again. And I want to say, actually, this entropy of y given x is, in my opinion, kind of bad notation. Or maybe it is good notation, but it's like misleading at first. Because it looks like it's somehow the entropy of a random variable y conditioned on x, but it's actually an expectation. And I'm going to leave this to you as an exercise. Again, it's just like writing down the formulas. But this conditional entropy of y given x, it's really an expectation of something. It's an expectation over, you draw like an outcome little x for x, and then having gotten an outcome little x for x, like heart or 0 or 1, you consider the random variable, which is y, but conditioned on capital X, the random variable, taking this value little x. So like if little x is heart, you know, you think of like, oh, now let's imagine the random variable y conditioned on x being heart, which is actually a simple random variable. It's just constantly heart. I don't know if you remember back my example with the hearts and zeros and ones and ABCD. So in that case, the entropy of that random variable is 0. But some other time, you know, x might be 1, little x might be 1, and then the random variable y conditioned on little x might just be uniform on ABCD, and that has entropy 2. So even though like this expression starts with an h, it's really like an expectation over the x outcomes of the entropy of a conditioned random variable. Okay, so we won't exactly need this later, but it's just something to watch out for. Okay. So the last thing I want to tell you is this is really like sort of a last definition of pure basic information theory things. And we're not going to really work with it, but I need to make it here so we can talk easily about another concept. It's just the conditional mutual information of x and y given z. So now you have 3 random variables involved. And it has like sort of the natural definition. So it's like, what is the mutual information? So you imagine x, y, and z are all intertangled, like they may all depend on one another. And you sort of imagine like, what is the, on average, like once you draw and learn or condition on a value for z, now what is the mutual information between x and y? So I'll do an example in a moment. But at the level of formulas, it's like, it's the same definition as the mutual information between x and y, except you stick a condition on z everywhere. So now that we know how to define conditional entropy, we can, you know, plug it into the definition for mutual information and get conditional mutual information. And again, just like with the conditional entropy, this is really an expectation. It's, again, like you draw an outcome little z for capital Z, and then you consider like, okay, how does that change the random variables x and y? X and y may still be dependent, but their distributions might sort of change now that you've conditioned on capital Z being little z. You measure the mutual information of those random variables, and then you like take the expectation or the average over the draw from z. So let me do an example that hopefully will clarify. And again, I'm going to ask you to fill in these blanks here. So this is the definition of conditional mutual information. And let me give an example here where we have 3 random variables. And it's a classic scenario in probability. X and Y are independent random bits, and Z is their parity, or their XOR, or their sum mod 2. This is a classical example of like 3 random variables, random bits in fact, where they're not collectively independent, but any pair of them is independent. Okay? These are pairwise independent bits. So, right, so what is the mutual information between X and Y? Does anybody want to say in the chat? 0, very good, that's right. So if you just ignore Z in your life, just, you can draw X and Y and Z all together, but just throw Z in the garbage, then X and Y are just independent random bits. And we know if you have 2 random variables, the mutual information is 0. There's no savings that you can get, so yeah, 0. But on the other hand, what is the mutual information between X and Y conditioned on Z? Someone can say 1. Very good, that's right. Because basically, in fact, no matter the outcome of Z, if Z is either 0 or 1, once you condition on that, X and Y go from being independent to being highly dependent, right? So I mean, if you condition on, let's say, this XOR being 0, then that's exactly telling you that x plus y mod 2 is 0, so x equals y. So now x equals y, and the mutual information between two equal random variables that are just a random bit is 1. And conversely, if z happens to be 1, then you totally know that x and y are opposite random bits. And again, the mutual information between two definitely opposite uniformly random bits is 1. Okay, so that's true. That's a fact. And it might be considered counterintuitive, but that's life, that like conditioning on a random variable can make the mutual information go up, but it's sort of true. And this also implies that there's like no, I mentioned before that once you have 3 random variables, these like Venn diagrams of information like can't really make sense. Because, imagine the only thing you knew about in life were x and y. And they're independent random bits, so they have 0 mutual information. So you'd be like, all right, well, I'll draw that Venn diagram. Here's x. And they have no mutual information, so they're non-overlapping Venn diagrams. There's y. On the other hand, if you think about just, let's say, x and z in isolation and forget about y, then x and z are also independent random bits. So you'd be like, oh, the x and z have no mutual information, so I better draw like an empty Venn diagram between x and z. And similarly, an empty Venn diagram between y and z. Right, but there is, this would sort of, the picture somehow suggests that they're all like independent and there's like no mutual information at all. But, condition on z, there is mutual information between x and y. So there's no way to like capture it with a Venn diagram. So that's life. Yeah, the Venn diagrams are just an intuitive aid when you have 2 random variables. Okay, great. So if you have any questions, do chat them. Somebody says this is a one-time pad. How is it a one-time pad? It's kind of like if you're saying if like your message x is like 1 bit and you're like, oh, I'm going to encrypt this message by XORing it with like a random one-time pad y. Maybe so. And then so z looks totally random and it's independent of x. But like, yeah, if you know y, yeah, I guess I see what you're saying. Like, it'd be more like a, yeah, it'd be more like a one-time pad if we like just had a z here. If we wrote z here, it's all the same. And we condition on y here. And then it'd be like saying like, oh yeah, like, there's no mutual information between the message x and like the encoding z when y is a random one-time pad. But yeah, like the mutual information between x and z is perfect if you condition on like knowing the one-time pad y. Does conditioning only increase mutual information? No, it can increase it or decrease it. Yeah, it can go either way. Is there a quick example I can think of for it decreasing mutual information? Yeah, well, like imagine, I don't know if you, since I've worked with these slides before, I like remember that heart example very well. But if in that case with x and y, where x and y, they're either both heart with probably a half, or else they were like independent, like x was a random bit and like y was a random letter between a and d. Let's see, the mutual information between x and y there was 1. But if you let z be the let's say indicator random variable that x and y are both heart, then condition on z, whether they are both heart or are not both heart, they become independent, independent or constant. So that would mean their conditional mutual information is 0, even though the original mutual information was 1. I think I got that example right. If I made a mistake, let me know. Okay, good. So that's all I wanted to say about mutual information. And now we're going to take a bit of a left turn from the point of view of very classical information theory. But, this is a CS Theory Toolkit. So I want to now connect this to a topic in CS theory, namely the one we talked about in the last lecture, communication complexity. So there was like a great renaissance in like using like information theory to make big strides in communication complexity about 10 years ago. So I want to tell you about a little bit of that now. 10 to 15 years ago, 5 to 15 years ago. Okay, Okay, so today so far, I mean, if you think about communication, we sort of thought about implicitly like one-way communication when you have a probability distribution on input. So like when we were even defining entropy, yeah, when you're even defining entropy, we imagine that like maybe Alice gets a random variable X and she's now going to try to communicate its value to Bob using bits, and she's going to try to communicate it using as few bits as she can on average. And if you remember the last time when we were talking about communication complexity, you know, we were talking about randomized communication complexity because it's kind of the interesting form of communication complexity. Well, quantum is interesting too, but we'll stick with randomized communication complexity. And the first model of randomized communication complexity, the one we actually care about most, is where like it's worst case model over inputs, but Alice and Bob are allowed to use randomization to like try to minimize the amount of bits they communicate. But we saw like the main way you try to prove lower bounds on that is by looking at distributional communication complexity. And anyway, distributional communication complexity is interesting in and of itself. So distributional communication complexity, you have Alice and Bob, and they're trying to compute some function f, or do some task with their inputs f. And we do imagine that their inputs x and y are random from some distribution, so not necessarily independent, but we imagine that x and y get a random, possibly dependent inputs. And then once they have random inputs, you can actually, it's without loss of generality to only worry about Alice and Bob using deterministic protocols. So we're going to talk about, we talked about deterministic protocols in the context where you have random inputs. And this is like a little SAT analogy, not like the SAT like satisfiability problem, but like the tests in high school. It's like, we have like a colon here and like a colon here and like a double colon here. So in the simple one-way communication problem with distributions on the inputs, we talked about average communication cost, and we kind of related this number, entropy. And we saw that, there's a sort of a one-way relationship, the average communication cost. Actually, I never mentioned this, but it has to be at least the entropy, and it's at most the entropy plus 1. And we sort of saw that they were in fact the same if you were allowed to like amortize. And yeah, so now you can ask for a similar sort of story where, instead of just one-way communication and like one input, you have communication complexity, like two-way back and forth communication. And they're sort of like the optimal cost for solving like a problem, or f, or computing a function f, under the assumption of like using, or the inputs coming from the distribution mu, and making error epsilon was some number. This is like the distributional communication complexity of f under distribution mu. And it turns out, the right information type construct number for two-way communication is this quantity called information complexity. So that's what I want to tell you about in the last 20 minutes. So let's first remember a little bit about this distributional communication complexity. So recall the setup. We have Alice and Bob, and they want to compute some function f of their mutual inputs, little x and little y. And they're going to use a communication protocol pi, which is, some system whereby they understand who will communicate which bits next and how they'll send communication bits based on their inputs, little x and little y. And pi does not necessarily have to always compute the function f. We're going to have error when we have randomized communication complexity. And we also imagine we have this mu, which is a joint distribution on inputs for both x and y. And we'll say that the error of protocol pi under distribution mu is just the probability that Alice and Bob come to the wrong answer. So this pi of xy is sort of the final answer they agree on. And it's supposed to be f of x and y, but it might not be. And the probability of these failing to be the same thing under mu is the error. And finally, the distributional communication complexity of function f under distribution mu with error rate epsilon, whoops, that was a mistake, is the least communication cost of a deterministic protocol pi that achieves error at most epsilon. Okay, so that's a recap from last time. So let's put that in a box. And now I'll tell you this thing, information complexity, which is ultimately going to be like a number associated with f and mu and epsilon. That's kind of like the information theoretic heart of this problem. Okay, so the information complexity of a protocol pi under a distribution mu is this. Okay, it's the sum of two terms that are kind of symmetrical looking. The first term is the mutual information of the random variable pi and the random variable y condition on x. So this is using that last most complicated definition, the conditional mutual information. So x and y are Bob and Alice's, well, Alice and Bob's inputs. And I'm kind of abusing notation a little bit here. Pi is a deterministic protocol. But here, what I really mean by it in this expression is I want to think of it as a random variable, but it doesn't take on numbers. It takes on like transcripts as its values. And so pi represents, imagine you like drew the inputs for Alice and Bob, x and y, little x and little y, and then you like gave them to Alice and Bob and let them talk according to this communication protocol pi. They would output like a stream of messages back and forth. And the whole transcript of what they output, not their inputs, but just the transcript of what they output is the random variable pi. Okay, and so this quantity, conditional mutual information of pi and y conditioned on x, it has an intuitive meaning. And the intuitive meaning is the amount of information the conversation teaches Alice about Bob's input. So Alice, remember, knows x. Alice gets x. And so from her point of view, she sees this random variable pi, which is partly determined by x, and it's partly determined by y. And she sees pi, but she doesn't know Bob's input y. And so this mutual information, conditioned on what she knows, is kind of quantifying the sort of bits of information Alice learned about Bob's input at the end of the conversation. Okay, and similarly, the second term is the amount of information that Bob learned about Alice's input, sort of the amount of information in bits that Bob learned about Alice's input at the end of the conversation. Okay, and so the information complexity of pi under this distribution is the sum of these two information amounts. And I'll explain a little bit more intuition on that in a second, but let me just say now that this is sort of an abuse of notation too, but the information complexity of the problem or function f under distribution mu with error epsilon is sort of like imagine like Bob and Alice still want to solve the same task as before, but instead of trying to minimize the communication, the number of bits they send back and forth, they instead try to minimize this informational quantity. They try to minimize the sum of these two information amounts. So the protocol, which you look at the protocol which minimizes this amount of information, the amount of information that it creates among all protocols that achieve error at most epsilon is called the information complexity of f under distribution mu. And one thing I should have said before is like it's sort of the case, it's much in the same way that like well, I think I have it here on the next bit. This intuitive fact, much in the same way that like any successful protocol for transferring or transmitting, a draw from X uses at least entropy of X bits. Similarly, any communication protocol which achieves error epsilon on distribution mu must send a number of bits in total, which is at least this information information complexity. And the reason is like, this is the number of bits that Alice learns about Bob's input from at the end of the conversation. And like, she already knows the whole transcript and she knows her own input X. So the only way she gets information about Bob's Y is through like the bits that Bob sent to her. And the only way Bob gets information about Alice's input X is through the bits that Alice sent to Bob. So the total communication, which is the sum of these two things, bits Alice sent to Bob and bits Bob sent to Alice, intuitively has to be at least the information complexity of the protocol. And that's a not hard fact to prove. I should also mention a funny mathematical thing. You cannot formally write min here. You actually have to write infimum, if you remember that is, because it can definitely be the case that for a fixed problem or function f, and a fixed distribution mu, and a fixed error term epsilon, there's no one deterministic protocol that like sort of solves the problem with error at most epsilon, but uses the least amount of, or conveys the least amount of information. It could be that like you have a series of protocols that all, convey less and less and less and less information, because you're not putting any upper bound on how many actual bits of communication they have. So you could like imagine like Bob and Alice, who are extremely guarded, and like they very slowly exchange some like actual bits of information that are bits of communication that are not too revealing about information. And so that's why at a math level, you have to take this infimum, the least lower bound, greatest lower bound. Okay. Right, so you can compare this, as I said, to this much simpler fact that if you want to, Alice wants to one-way communicate a draw from X to Bob, she needs to communicate at least entropy of X bits. And you might start thinking about the converse, like, is the reverse true? Like, can you always communicate not much more than this information complexity number of bits? Maybe if you allow amortization? Well, we'll get to that. So this information complexity, it's like a kind of a new concept. It was only really first defined in this paper from 2004 by Bar Yosef, Jairam Kumar, and Siva Kumar. And they proved in this paper one beautiful theorem about it, which is that it's perfectly additive. And this is like the analog of the fact that like the entropy of a bunch of independent random variables is the sum of the entropies of those random variables. So it's a more complicated fact. It says, okay, let's say you have some function f that you're trying to compute, and some target error epsilon, and some distribution mu. So that's like one problem. Now imagine that like, Alice and Bob were like, hey, you're gonna have to solve f n times, and you're gonna get n independent inputs, like, so, x1 and y1 will be drawn from mu, so they're not independent, but they are independent from x2, y2, and from xn, yn. So this mu to the, I don't know, O times n means make n draws from the joint distribution on inputs, x and y mu. And this f with like the superscript power n means they're trying to solve all these communication problems and figure out f of xi, yi, simultaneously with error at most epsilon for all the coordinates. So they get all the inputs, like Alice gets x1 through xn, Alice gets x1 through xn, Bob gets y1 through yn, and they have to figure out all the pairwise answers with error at most epsilon. You can again ask like how many bits of communication do they need, and how much information do they need? And it's a funny thing that like actually you might think like, well, they're independent instances. What can they do except like run the protocol, communication protocol n times? But they can do better than that. And it's similar to what we saw with communication, right? I mean, if you have to transmit one trit from Alice to Bob, okay, then, there's a bit of waste. And the best thing you can do involves, 2.6 bits on average. But if you're going to be solving this problem n times, like transmitting n copies, then you can like look at all the n tasks you have, somehow collate them together and get some savings. And that can also be true in this context of two-way communication complexity problems. But just like with entropy, like if you go to this refined measure that doesn't, that doesn't have to be an integer, that really measures like the real number amount of information, and they showed that it's like perfectly additive, like the amount of information you need to, that, Alice needs to learn about Bob's input plus Bob needs to learn about Alice's input to solve this problem f on like n independent instances is really n times the amount you need for a single instance. So that's cool. So in particular, since we have this intuitive fact that the communication cost is at least the information cost, it tells you that like the communication cost for solving n independent instances of like function f on n pairs xi, yi, with error epsilon on each pair, is at least n times the information complexity. And so this could be a route potentially to proving, lower bounds on randomized communication complexity, which in general can be quite tough. So let me save this fact up here. And I should say that like now I'm going to start telling you things at sort of a bit of a high level, and I will not be like 100% precise in I think I will be precise. I think I won't tell you anything that's wrong, but like I'm going to hide some details. So remember last time, we talked about sort of the 3SAT of the communication complexity world, the disjointness problem. It was sort of this really hard problem. X and Y are strings, maybe representing subsets of the numbers 1 through n, and Alice and Bob have to tell if their subsets are disjoint or not. Or if you think of them as strings and you like stack them on top of each other, they want to tell if there's any coordinate where they both have a 1. They want the opposite to that answer. So really, like, they do like a sort of a pairwise AND of their two strings, and then they want to see if there are any coordinates between 1 and n where that pairwise AND is a 1, and then because it's disjointness, you take the negation, but never mind. And we saw that, I told you it's a true but very difficult to prove theorem that even if Alice and Bob can be randomized, the communication complexity needed for this is linear in n. They can't do much better than just Alice sends her whole string to Bob. But a good way to prove it, as I suggested last time, is through this information theory. And you see, it's kind of similar. So it's kind of like Alice and Bob have to solve n copies of like a teeny tiny problem of computing the AND between like a bit of Alice and a bit of Bob. It's not the same because like in this notation, really they have to compute n bits. They have to compute all the n answers, all the n ands. And in disjointness, you really only need to compute the or of the answers. You don't have to actually compute all the answers. But this is where I'm saying I'm going a little bit vague. I mean, this problem is pretty similar to like solving n independent instances, potentially, of a very simple problem, f equals the 1-bit AND function. And so if you want to use this, then you also need to have a probability distribution on inputs for disjointness. That's a product distribution. But it's like a product distribution across pairs. Okay, so you might ask yourself, okay, if the n bits, let me just put this up. So Alice is eventually going to get a string, and Bob is eventually going to get a string. And in this mindset, you're really interested in like, okay, we're going to have some probability distribution on their mutual first coordinates and some probability distribution on their mutual second coordinates. And we're going to use the same distribution for every pair of coordinates. But what distribution should we put on those pairs of coordinates to make it a challenge for Alice and Bob? So if we're trying to prove like a cool lower bound, we want to sort of think of a distribution that's going to make it hard as possible for Alice and Bob. And I'm going to ask you in a moment to think about that. So, well, that moment, I guess, is sort of now. So if you're trying to design a probability distribution on pairs of bits, mu, so you have to come up with 4 numbers, the probability of plugging in 0, 0, 0, 1, 1, 0, and 1, 1. And you want to make it tough on Alice and Bob for the point of view of them trying to decide if their sets are disjoint or if their strings have like a position where they have a 1 in common. What kind of choice for mu might you make? Notice, by the way, that this way of doing things gives strings for x and y for Alice and Bob that are not independent. The strings are not independent. The pairs of coordinates are independent. So one suggestion was that you could make mu be independent. So that would be like saying like, okay, I'm going to do a quarter, a quarter, a quarter, a quarter. And that actually corresponds to like x and y just being independent uniform strings. Thing is, at least intuitively, this does not make it too hard for Alice and Bob, because if Alice and Bob both get, completely random strings, then, 99% of the time, we're in fact like 1 minus 2 to the minus n of the time, the answer is going to be no, the strings are not disjoint, because like you have a quarter chance of having a column that's 1, 1. So like, probably you're going to have some column that's 1, 1. So this is not going to make it too hard on Alice and Bob. They can use the deterministic protocol that just always says no. And like they'll achieve an error that's like 2 to the minus, or 4 to the minus, maybe 3/4 to the n. Something like that, right? It'll be exponentially small. Somebody else suggested half, 0, 0, a half. Okay, that's interesting too. Here, let me get this one out. Let's think about it. Half, 0, 0, a half. Actually, this is not so good because basically, anytime you have, this is eventually the point I want to make, Maybe, yeah, somebody else suggested this too. Let's try the other thing. Let's try 0, half, 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 0. So what about this? Is this going to make it hard for Alice and Bob? Well, yeah, this one is not exactly going to be hard because actually, if Alice and Bob know that like this, then they actually know that they'll never be disjoint. So that's not so good. They can just always happily answer yes. Okay, we have another suggestion of 0, 1, 1, and 1 over n normalized. Yeah, I like it. 0. Let's think about this one. So the suggestion here is, let's put like 1 over n here. And that's actually a pretty good idea. And 1 and 1 here, or like maybe whatever, 1 minus 1 over 2n, but basically 1. So a good thing about that is, with this being 1 over n, basically, you know, there's like going to be a constant chance that you'll have 1 or more 1, 1, so that, you know, the answer is sort of roughly equally likely to be 0 or 1, which is good at making it hard on Alice and Bob. This is reasonable. It actually doesn't hurt and may help to put some probability on here as well. But the main thing I want to get out of this discussion is, yeah, like the main thing is just to make sure you put like almost 0 probability on 1, 1, although not literally 0 probability. So the main answer I want to take away from this is, you know, lots of mu's could be fine, but like mu of 1, 1 should be very close to 0. And here is another cool theorem. This one is hard, but true. And it says the following. It's kind of transforms this theorem into something that's like exclusively about like basically what happens if you do combining, not with you got to compute all the answers, but you got to compute the OR of the answers. They show that the communication complexity for disjointness when you use this n-fold copy of mu distribution is at least n times basically the information complexity of computing the and function under with 0 error under your distribution mu for any mu that has exactly 0 probability on 1, 1. Which is a bit funny, but this is the theorem that you can prove. And so, for example, you can take this distribution that's like 1/3, 1/3, 1/3, 0. And then it's funny, you just have to ask yourself, okay, like a question about like, you know, 1-bit communication problem or an information theory problem. If Alice and Bob both get a bit, they have to have error 0, so they need a protocol that correctly determines 100% of their time if their bits are both true, if they satisfy and. And now the story is, 1/3 of the time they're getting 0, 0, 1/3 of the time they're getting 1, 0, 1/3 of the time they're getting 0, 1. And they're never actually getting 1, 1, but they still have to have a protocol that would be correct if they were getting 1, 1. You know, what's the least information they can communicate in some sense? What's the least amount that Alice needs to learn about Bob's input plus Bob learning about Alice's input to decide the and function? This is actually, even though it's a problem about like 1 bit, it's actually surprisingly challenging. But with a lot of effort, you can figure out the answer. It turns out to be 1 over 3 ln 2, which is about 0.48. And once you know this theorem, you plug it in and you get that there exists some epsilon greater than 0. And this distribution, the n-fold product of this 1/3, 1/3, 1/3, 0 distribution, such that under this distribution, any protocol for solving disjointness with error epsilon needs at least 0.48 n bits of communication. And then by Yau's principle, you get that the randomized communication complexity of disjointness is at least 0.48 n. So that's how you can prove it. It's actually 0.482 something. That's like slightly better to take a number that's like slightly different than 1/3, but close enough. Okay, so that's sort of story time about this. And let me just end with a little bit more story time of like one more slide or 2 more slides. So this is an old slide we saw with beautiful theorem number 1 about the exact additivity of information cost and how you can use that to like get a lower bound for communication bits of communication in terms of information complexity. And if we just take this inequality and divide it by n, we get this quantity. And we do that because we're thinking about amortization. You know, how much does it you need to communicate on average if you have to do n copies of some compute f task? So I'll put that all up here. And so this is true for every n. And so in particular, it's true in the limit as n goes to infinity. And I say that because this quantity here is really what you might define to be the amortized communication cost under distribution mu. Like, you know, if you're getting inputs from distribution mu, you're trying to, Alice and Bob are trying to communicate to solve f, and they're going to get like a really large number of copies of this task, n independent copies. You can look how much bits they communicate, divide by n, and say like, okay, that's their amortized communication cost. We know that it's at least the information cost for, you know, just doing this one time. And so you might ask about the other direction. And that's beautiful theorem number 2 is proved sort of independently by Ma, Ishwar, and Gupta from the information theory community, and Braverman and Rao from the CS theory community. And they showed that they're equal. So it's exactly like with entropy capturing, like, you know, average case one-way communication. The average case, you know, two-way communication cost of solving a problem f when amortized out is exactly this information complexity quantity. And I'll just end by saying one word about the proof. You see what you have to do to prove the upper bound is you need to actually exhibit like a communication protocol, which really takes advantage of amortization, and takes like maybe a protocol that has like a lot of communication, but, you know, not so much information being conveyed, and compress it into like a short communication. And they do this. And so like their theorem kind of shows that any conversation that, even though it takes a long time, that conveys very little information, may be compressed to a short one, which is really, I mean, that's like that's deep. I mean, if you think about it, like that's a metaphor, yeah, for maybe these lectures or like just general conversing with people, like a lot of words sometimes, and you want to compress that down to just the right amount of information. Okay, so that's it. I shall see you again on Tuesday. I'll stop the recording now, but I'll stick around to answer questions.